Right now, as you listen to this, you are falling. Not just through the gravity well of our sun or the spiral arms of the Milky Way, but through a vast, incomprehensible emptiness. A hole in the universe so immense it defies our most fundamental understanding of reality. For decades, the maps of the cosmos we've drawn have been wrong. They've shown us a universe that is, on the grandest scale, smooth, uniform, and predictable. But the truth, the one that scientists are only now beginning to admit, is far stranger and far more unsettling. We are not in a typical patch of the cosmos. We are, in fact, suspended near the very center of a colossal, 2 billion light-year-wide bubble of nothingness. A region so sparse in matter that it shouldn't exist according to the standard rules of physics. It's a cosmic secret, a hidden truth about our place in the universe that changes everything we thought we knew about the Big Bang, dark matter, and the ultimate fate of the cosmos. The implications of this emptiness are staggering. It suggests that the very fabric of space and time around us is being stretched, that the laws of physics are being subtly warped, and that the greatest crisis in modern cosmology, the Hubble Tension, might be nothing more than a local illusion caused by the fact that we are, quite literally, living in a void. And if that thought has already sent a shiver down your spine, if you're already asking yourself how something this huge could remain hidden, then you're in the right place. This is CosmoDepth, and we are about to journey into the KBC Void, the colossal, silent, and nearly empty region of space that we call home. If you want to join us on this journey, if you want to explore the deepest, most mind-bending secrets of the universe, then take a moment, hit that like button, and subscribe to the channel. It's the easiest way to ensure you don't miss the next time we peel back the curtain on reality. The story of the KBC Void, or the local hole, as it is sometimes called, is not a story of discovery in the traditional sense, but a story of realization. It's the moment astronomers looked at their data, looked at their maps, and noticed a silence where there should have been a chorus. For most of the 20th century, the prevailing cosmological model, the one that still dominates our textbooks, is based on a profound, almost philosophical principle, the Cosmological Principle. This principle states that on scales larger than a few 100 million light-years, the universe is homogeneous and isotropic. In plain language, that means it looks the same everywhere, and in every direction. If you were to take a gigantic cosmic ruler and measure the density of matter, galaxies, stars, gas, and dark matter in one region of the universe, that measurement should be roughly the same as any other region. This assumption is the bedrock of the lambda-CDM model, the mathematical framework that successfully describes everything from the Big Bang to the formation of the first stars. But the cosmological principle, for all its elegance, is an assumption, a necessary simplification to make the math work. And like all assumptions, it is vulnerable to the messy, complicated truth of observation. The first cracks in this perfect picture began to appear not with a telescope, but with a ruler, a cosmic ruler known as the Hubble constant. The Hubble constant, often represented as H0, is the single most important number in cosmology. It measures the rate at which the universe is expanding right now. If you know H0, you can calculate the age of the universe, its size, and even its ultimate destiny. For decades, scientists have been trying to pin down this number with ever-increasing precision, and for decades they've been failing. The failure, however, is not one of technology, but one of fundamental disagreement. There are two primary ways to measure the Hubble constant, and they give two very different answers. The first method uses the early universe, specifically the cosmic microwave background, or CMB. The CMB is the faint echo of the Big Bang, a snapshot of the universe when it was only 380,000 years old. By analyzing the tiny temperature fluctuations in this ancient light, cosmologists can use the lambda CDM model to extrapolate the expansion rate of the universe today. This method, primarily using data from the Planck satellite, gives a value of approximately 67.4 kilometers per second per megaparsec. This is the early universe value. The second method uses the local universe, relying on what astronomers call the cosmic distance ladder. This involves measuring the distances to nearby galaxies using standard candles, like Cepheid variable stars and Type 1a supernovae. These are objects with a known intrinsic brightness, allowing astronomers to calculate their distance by how dim they appear to us. By measuring the distance to these galaxies and the speed at which they are moving away from us, we get a direct local measurement of the expansion rate. This method, using data from the Hubble Space Telescope and other local surveys, consistently yields a value of around 73.0 kilometers per second per megaparsec. This is the local universe value. The difference between 67.4 and 73.0 might seem small, a mere 5.6 units, but in the precise world of cosmology, this is a catastrophic disagreement. It's a fundamental conflict, a 5 sigma statistical anomaly that has been dubbed the Hubble Tension. It's not a measurement error. It's a sign that something is profoundly wrong with our understanding of the universe. It suggests one of 3 possibilities. Either there is new, unknown physics in the early universe, new, unknown physics in the late universe, or, and this is where the KBC Void enters the picture, that the cosmological principle itself is flawed, and our local neighborhood is simply not representative of the universe as a whole. Enter the KBC Void. KBC stands for Keenan, Barger, and Cowie, the astronomers who first meticulously mapped this region and realized the true scale of the anomaly. What they found was not a small, insignificant bubble, but a gargantuan, spherical region of space extending out to about 1 billion light-years in every direction from the Milky Way. This is the local hole, and its defining characteristic is its astonishing lack of matter. Imagine the universe as a sponge, a vast, frothy network of filaments, walls, and clusters of galaxies separated by enormous, empty bubbles. This is the cosmic web. Our Milky Way galaxy is located in a cluster called the local group, which is part of a supercluster called Laniakea. Laniakea, in turn, is part of a larger structure. But what the KBC team realized is that our entire local supercluster, Laniakea, is nestled deep inside one of the largest voids ever discovered. The density of matter inside the KBC void is estimated to be about 20% to 50% lower than the cosmic average. This is not a slight dip, it's a profound deficit. It means that for 1 billion light-years in every direction, the universe is emptier than it should be. And this emptiness, this lack of gravitational pull, is the key to resolving the Hubble tension without invoking any new, exotic physics. The argument is deceptively simple. Gravity pulls, and a lack of matter means a lack of gravity. If our local universe is surrounded by a shell of denser, more massive structures, then the matter inside the void, including our Milky Way, would be pulled outward, toward the surrounding walls. This outward pull would cause the space inside the void to expand slightly faster than the space outside the void. Think of it like being in a boat in a large, calm lake. If the lake is perfectly uniform, your boat moves at a steady speed. But if you are in a low-density bubble of water surrounded by a ring of denser, heavier liquid, the denser liquid pulls the water away from you, causing your boat to accelerate outward. For us, this localized, slightly faster expansion rate is exactly what the local universe measurement of the Hubble constant is detecting. The value of 73.0 is not the true universal expansion rate, it's the expansion rate of our local void. The value of 67.4 derived from the early universe is the true universal expansion rate. The Hubble tension in this scenario is not a crisis of physics, but a crisis of location. We simply happen to live in a cosmic anomaly. But the KBC Void is more than just a convenient explanation for a cosmological problem. Its very existence is a challenge to the cosmological principle and the lambda CDM model. How could such a massive 2 billion light-year wide structure form in the 13.8 billion years since the Big Bang? The standard model suggests that while voids should exist, they should be much smaller, perhaps a few 100 million light-years across at most. A void of this magnitude is a statistical impossibility, a cosmic snowflake that shouldn't have been able to crystallize. This is where the story deepens, moving from a simple question of location to a profound inquiry into the nature of dark matter, dark energy, and the very seeds of the universe. The KBC Void is not just a hole, it is a laboratory, a colossal, empty arena where we can test the limits of our cosmic theories. To understand how this void came to be, we must first understand the cosmic web itself. Imagine the early universe, a hot, dense soup of particles. In this soup, there were tiny quantum fluctuations, slight overdensities and underdensities of matter. These were the seeds of all structure. Over billions of years, gravity acted on these seeds. The overdense regions attracted more matter, growing into the filaments and clusters we see today. The underdense regions, the voids, were slowly emptied out as their matter was pulled away by the surrounding gravity. The formation of structure is an ongoing process, a cosmic dance governed primarily by dark matter. Dark matter, which makes up about 85% of all matter in the universe, is the invisible scaffolding of the cosmic web. It doesn't interact with light, but its gravity dictates the movement of all visible matter. In the standard model, dark matter is considered cold, meaning it moves slowly and clumps together easily. This cold dark matter model is highly successful at explaining the formation of the filaments and clusters. However, the KBC Void presents a problem for this cold dark matter model. A void this large and this empty suggests that the process of emptying out was somehow more efficient, or that the initial conditions were far more extreme than predicted. Some scientists suggest that the existence of the KBC Void might point toward a different kind of dark matter. Warm dark matter. Warm dark matter particles would be lighter and faster moving than their cold counterparts. These faster particles would have smoothed out the smaller density fluctuations in the early universe, making it harder for small structures to form and potentially leading to the formation of much larger, emptier voids. The KBC Void, therefore, could be the first colossal piece of evidence that the dark matter we thought we knew is wrong. But the void's influence doesn't stop at dark matter. It also offers a radical alternative to the concept of dark energy. Dark energy is the mysterious force that cosmologists invented to explain the accelerating expansion of the universe. It's thought to be a uniform energy density inherent to space itself, pushing everything apart. It makes up about 68% of the total energy density of the universe. The alternative, known as the timescape cosmology, suggests that dark energy might be an illusion. This theory, championed by cosmologists like David Wiltshire, argues that because space expands at different rates in regions of different density, faster in the low-density voids and slower in the high-density walls, the way we measure time and distance is fundamentally skewed. In the timescape model, the universe is not homogeneous. The expansion we observe, the one we attribute to dark energy, is actually the average of the different expansion rates across the cosmic web. When we look out from our vantage point inside the KBC Void, we are looking out through a region that is expanding faster than the average. This localized, faster than average expansion rate gives us the appearance of a universal acceleration driven by dark energy. The universe might not be accelerating globally. We just happen to be in a region that is expanding locally at an accelerated rate. If this is true, then the greatest mystery of the universe, the nature of dark energy, vanishes, replaced by a simple yet profound question of perspective. The KBC Void, therefore, is not just a hole in space, it is a hole in the standard model of cosmology. It forces us to confront the possibility that the universe is far more lumpy, far more inhomogeneous than we ever dared to imagine. It takes us from the comfort of a smooth, predictable cosmos to the unsettling reality of a universe where our location fundamentally dictates our perception of reality. To truly grasp the scale of this emptiness, we need to zoom in from the cosmic web to our own neighborhood. The KBC Void is an umbrella term for a hierarchy of voids, and we are situated within the smallest, most local of them, the local void. This local void is about 150 million light-years across, and it is actively pushing our galaxy, the Milky Way, away from its center. Imagine standing on Earth and looking out into the night sky. Every star you see, every nebula, every neighboring galaxy like Andromeda, they are all part of a tiny, dense island of matter in an ocean of nothing. The local group of galaxies, which includes the Milky Way and Andromeda, is like a small raft in the middle of a colossal, empty sea. And as we look out, we see the evidence of this emptiness in the motion of our own galaxy. The Milky Way is not moving randomly. It is being pulled by the gravity of the surrounding structures, the massive Virgo cluster, the Great Attractor, and the Shapley supercluster. These are the dense walls of the KBC Void. But at the same time, we are also being pushed by the lack of gravity from the void itself. The void is not a passive empty space, it is an active participant in the cosmic tug-of-war, a region of negative gravitational pressure. This push and pull creates a phenomenon called peculiar velocity. Every galaxy has a velocity due to the overall expansion of the universe, the Hubble flow, but it also has a peculiar velocity, a local motion caused by the gravitational influence of its neighbors. The peculiar velocity of the Milky Way is a complex three-dimensional dance, but the overall effect is a movement toward the densest regions and away from the emptiest. Our motion is a direct, physical confirmation that we are not in a typical, uniform patch of the cosmos. Our galaxy is literally being swept out of the void. The most dramatic evidence for the KBC Void comes from an unexpected source, the kinematic Sunyaev-Zeldovich effect. This is a subtle distortion in the light of the cosmic microwave background caused by the movement of galaxy clusters. When a massive cluster moves, the electrons in its hot gas scatter the CMB photons, changing their energy. By measuring this effect, astronomers can determine the velocity of galaxy clusters. In 2017, a team of researchers used this effect to map the flow of matter out to 1 billion light-years. What they found was a massive outflow of matter from the region of the KBC Void, confirming the void's existence and its colossal size. The data showed that the matter in our local universe is not stationary. It is streaming away from the center of the void, being pulled toward the dense surrounding structures. This was the observational proof that the KBC Void was real, massive, and actively influencing the dynamics of our local universe. So, what does it truly mean to live inside a cosmic hole? It means our view of the universe is inherently biased. It means that every measurement we take, every observation we make, must be corrected for our peculiar, anomalous location. It means that the next great revolution in cosmology might not come from discovering a new particle or a new force, but from simply realizing that we are standing in the wrong place. The KBC Void is a cosmic paradox. It is a region of nothingness that explains everything. It resolves the Hubble Tension, it challenges the Cosmological Principle, and it offers a radical alternative to the mystery of dark energy. It is the ultimate cosmic blank canvas, a place where the laws of physics are tested, and where the most profound secrets of the universe might be hidden in the silence. We have only just begun to scratch the surface of this cosmic mystery. The sheer scale of the void, its impact on the expansion of space, and its challenge to the very nature of dark matter and dark energy are topics that demand a deeper, more detailed exploration. Let's take a moment to consider the sheer, mind-boggling scale, 2 billion light-years. To put that into perspective, the entire visible disk of our Milky Way galaxy is only about 100,000 light-years across. The KBC Void is 20,000 times wider than our entire galaxy. If you could travel at the speed of light, it would take you 2 billion years just to cross this empty expanse. It is a volume of space so vast that it contains more nothingness than the rest of the visible universe contains everything else. And yet, it is not perfectly empty. The void is not a perfect vacuum, and this is where the story gets even more interesting. It is a void of galaxies, but it is still filled with the fundamental ingredients of the cosmos: dark matter, dark energy, and a sea of nearly massless particles called neutrinos. The role of neutrinos in the KBC Void is a fascinating area of research. Neutrinos are often called ghost particles because they barely interact with matter. Trillions of them pass through your body every second, completely unnoticed. They have mass, but it is incredibly tiny, and they travel at nearly the speed of light. Because they move so fast, They don't clump together under gravity the way cold, dark matter does. They are almost uniformly distributed throughout the universe, including deep inside the voids. This uniform distribution of neutrinos means that even the emptiest regions of space have a subtle, pervasive, gravitational influence. The combined mass of all these fast-moving ghost particles acts like a gentle brake on the expansion of the void. By comparing the size and growth rate of voids in the early universe to the voids we see today, cosmologists can actually put a limit on the total mass of all the neutrinos in the universe. The KBC Void, in this sense, is a giant cosmic scale, weighing the ghost particles that permeate all of reality. If the void is growing slower than predicted, it could be a sign that the total mass of neutrinos is higher than currently estimated, once again using the emptiness to measure the invisible. But the most profound implication of the KBC Void is its challenge to the very concept of cosmic isotropy. Isotropy means the universe looks the same in all directions. If we are at the center of a 2 billion light-year void, then the universe is fundamentally not isotropic from our perspective. When we look out, we see fewer galaxies nearby than we should, and the light from distant objects has to travel through a region of space that is expanding at an anomalous rate. This affects our measurements of distance and velocity, leading directly back to the Hubble tension. The question then becomes, is it possible that our location is just a statistical fluke, a cosmic accident? Or does the KBC Void suggest a deeper, more fundamental flaw in the cosmological principle? Some radical theories suggest that the universe might be fundamentally anisotropic, meaning it has a preferred direction or axis. This is a deeply unsettling idea, as it would overturn the past century of cosmology. However, the KBC Void offers a more palatable, local explanation. The universe is isotropic on the largest scales, but we just happen to be in a massive, local fluctuation. It's like finding yourself in the middle of a colossal, perfectly round ocean wave. The wave itself is a local feature, but the ocean as a whole is still flat. The debate over the KBC Void and the Hubble Tension is one of the most exciting and contentious in modern science. It is a battle between two different ways of looking at the universe. The top-down approach, which uses the early universe, CMB, to predict the present, and the bottom-up approach, which uses local observations, supernovae, to measure the present. The void is the bridge, the potential link that reconciles these two seemingly contradictory views. If the KBC Void is indeed the explanation, it means our entire cosmic neighborhood, the one we have spent centuries mapping and exploring, is an outlier, a quiet, empty anomaly in a universe that is far denser and more structured than we perceive. It means that the true, average reality of the cosmos is something we can only glimpse indirectly through the ancient light of the Big Bang. The KBC Void forces us to confront the ultimate question of perspective. How much of what we call reality is simply a function of where we stand? If we were to suddenly transport ourselves to a dense wall of the cosmic web, where galaxies are packed tightly together, our measurement of the Hubble constant would be lower, and our perception of the universe would be different. The void is a profound reminder that in the cosmos, location is everything. But the void is not just a problem to be solved, it is a frontier to be explored. The next phase of this journey will take us into the heart of the void itself, to the few, lonely galaxies that reside within its depths, and to the strange, dark matter structures that must exist even in this colossal emptiness. We will explore the latest simulations that attempt to recreate the KBC Void, and we will look at the radical, mind-bending theories that suggest the void might be a window into the earliest moments of the universe, a relic of a time when the cosmos was even stranger than it is today. Stay with us. The silence of the void is about to reveal its deepest secrets. The existence of a void as immense as the KBC raises a critical question about the dynamics of the universe. How does matter behave in a region where gravity is so profoundly diminished? The few galaxies that do reside within the void, the so-called void galaxies, are not just lonely, they are strange. These void galaxies are the cosmic hermits. They are isolated, far from the gravitational influence of the massive clusters that populate the walls of the cosmic web. This isolation has a profound effect on their evolution. In the dense, crowded regions of the universe, galaxies constantly interact, merging, colliding, and having their gas stripped away. This interaction fuels bursts of star formation, but also leads to the eventual death of galaxies as their fuel is exhausted. Void galaxies, however, live a quiet, undisturbed life. They are typically smaller, fainter, and have a much higher proportion of cold gas, the raw material for star formation. Because they rarely interact, their star formation history is often a slow, steady burn, rather than the violent bursts seen in cluster galaxies. They are pristine, almost untouched relics of the early universe. Studying them is like opening a time capsule, offering a glimpse into how galaxies would evolve in the absence of external gravitational harassment. The most intriguing aspect of void galaxies is their potential to reveal the true nature of dark matter. In the dense regions of the cosmic web, the effects of dark matter are often masked or complicated by the overwhelming gravitational influence of visible matter and the violent interactions between galaxies. But in the quiet, low-gravity environment of the void, the subtle effects of dark matter become much easier to isolate. For example, the rotation curves of void galaxies, the speed at which stars orbit their galactic centers, can be measured with high precision. These curves reveal the distribution of dark matter in the galaxy's halo. If the KBC Void is truly a region of lower than average density, it should affect the dark matter halos of the galaxies within it. The halos might be less massive, more diffuse, or have a different shape than those in cluster galaxies. Any deviation from the standard dark matter model in these pristine environments would be a powerful clue about the particle's true nature. Furthermore, the void offers a unique testing ground for alternative theories of gravity, such as modified Newtonian dynamics, MOND. Mond proposes that the laws of gravity change at very low accelerations, eliminating the need for dark matter. In the low-gravity environment of a void, the accelerations experienced by stars in void galaxies are among the lowest in the universe, making them the perfect natural laboratory to test the MOND hypothesis. If Mond can successfully explain the rotation curves of void galaxies without invoking dark matter, while the standard lambda CDM model struggles, it would be a major victory for the alternative theory. The KBC Void, therefore, is not just a passive hole. It is a dynamic, evolving region of space that is actively shaping the evolution of the few structures within it. It is a place where the fundamental laws of physics are pushed to their limits, and where the most elusive components of the cosmos, dark matter and neutrinos, might finally reveal their secrets. But the greatest mystery remains. How did the KBC Void get so big? The standard cosmological model struggles to explain the formation of a 2 billion light-year void in 13.8 billion years. The most common explanation is that the void is a statistical extreme, a rare fluctuation in the initial conditions of the universe. Imagine flipping a coin 1 trillion times. You expect roughly half heads and half tails, but there is a tiny, non-zero probability that you might get a run of 1,000 heads in a row. The KBC Void could be the cosmic equivalent of that 1,000-head streak, a highly improbable, yet not impossible outcome of the random quantum fluctuations that seeded the universe. However, the sheer size of the void has led some scientists to explore more exotic explanations, theories that suggest the void is a relic of a time before the Big Bang itself. One such mind-bending idea involves the concept of cosmic inflation. Inflation is the theoretical period, just a fraction of a second after the Big Bang, during which the universe expanded exponentially, smoothing out all the initial lumps and bumps. The quantum fluctuations that existed before inflation were stretched to cosmic scales, becoming the seeds of the cosmic web. Some theories of inflation suggest that the expansion was not perfectly uniform across the entire universe. Imagine a vast inflating balloon, but with certain regions inflating faster than others. The KBC Void could be a region that experienced a slightly lower rate of inflation than its surroundings, or perhaps a region where the inflationary field decayed slightly earlier. These subtle differences in the early exponential expansion could have been magnified to create a 2 billion light-year-wide deficit of matter today. The void, in this context, would be a fossil, a direct imprint of the physics of the very first moments of the universe, a window into the pre-Big Bang era. Another radical possibility is that the KBC Void is a remnant of a cosmic string. Cosmic strings are hypothetical, one-dimensional topological defects that could have formed during a phase transition in the early universe. They are incredibly dense, thin lines of energy that stretch across the cosmos. While the existence of a string itself would create a gravitational pull, the space around the string could have been cleared out, creating a massive, empty region. While there is no direct evidence for cosmic strings, the scale of the KBC Void makes it a compelling candidate for a structure that could only be explained by such exotic, early universe physics. The KBC Void is, therefore, a challenge to our entire cosmological framework. It forces us to ask, is the universe truly as simple and uniform as the cosmological principle suggests, or is it a far more complex, lumpy, and statistically improbable place? The answer to this question will determine the next century of cosmological research. The journey into the void is a journey that has profound implications for the ultimate fate of the universe. The standard model predicts that the universe will continue to expand, driven by dark energy, eventually leading to a big freeze, where all stars die out and the universe becomes a cold, dark, and empty place. But if the timescape cosmology is correct, and dark energy is an illusion, then the ultimate fate of the universe might be very different. If the global expansion rate is slower than we currently measure, and if the density of matter is higher than we perceive, then the universe might not be headed for a big freeze. It might instead be headed for a big crunch, where gravity eventually overcomes the expansion and the entire cosmos collapses back in on itself. The KBC Void, this colossal bubble of nothingness, holds the key to the ultimate destiny of all things. It is a profound paradox. The greatest emptiness in the universe might contain the answer to the greatest question of all. How will it all end? As we conclude this deep dive into the KBC Void, we return to the most personal question of all. What does this mean for us here on Earth, in the tiny, dense island of the Milky Way? It means that we, the inhabitants of CosmoDepth, are privileged. We are living in a cosmic anomaly, a unique vantage point that gives us a skewed, yet incredibly insightful, view of the universe. Our location, far from being a problem, is a gift. It is the very reason we are forced to question the standard model, to look deeper, and to realize that the universe is far stranger and more beautiful than we ever imagined. The next time you look up at the night sky, remember the silence. Remember the vast, 2 billion light-year-wide emptiness that surrounds us. Remember that you are falling through a hole in space, and that this emptiness is the key to unlocking the deepest secrets of the cosmos. The KBC Void is a cosmic monument to the power of gravity and the sheer scale of the universe. But to truly appreciate its significance, we must move beyond its mere existence and delve into the specific measurable effects it has on the light that reaches us. This is where the concept of the integrated Sachs-Wolf (ISW) effect becomes crucial, offering an independent and highly technical line of evidence for the void's reality. The ISW effect is a subtle phenomenon related to how photons, particles of light, travel through the lumpy gravitational landscape of the universe. When a photon enters a massive structure, like a galaxy cluster, it gains energy. As it leaves that structure, it loses energy. In a static, non-expanding universe, the energy gained would perfectly equal the energy lost, and the photon's temperature would remain unchanged. However, the universe is expanding, and this expansion changes the equation. As a photon travels through a gravitational potential well, a massive cluster, the well itself expands during the photon's transit. This expansion means that the well is slightly shallower when the photon leaves than when it entered. Consequently, the photon loses less energy on the way out than it gained on the way in. The net result is that the photon gains a tiny amount of energy, appearing slightly hotter than it should. This is the positive ISW effect, and it is a direct signature of the universe's accelerating expansion driven by dark energy. The opposite happens when a photon travels through a cosmic void, like the KBC Void. A void is a gravitational hill, a region of lower than average potential. As a photon passes through the void, it loses a tiny amount of energy, making it appear slightly colder. This is the negative ISW effect. The KBC Void, being so vast and so close, should leave a colossal, cold imprint on the cosmic microwave background, the ancient light that bathes the entire sky. Astronomers have indeed searched for this cold spot, and while the results are complex and often debated, there are strong indications of a large-scale underdensity in the local universe that aligns with the predicted location of the KBC Void. The detection of this negative ISW effect would be a smoking gun, not just for the existence of the void, but for its profound impact on the large-scale structure of space-time. It would mean that the KBC Void is not just a hole in the distribution of galaxies, but a massive, gravitational anomaly that is actively reshaping the energy of the oldest light in the cosmos. It's a subtle, almost imperceptible whisper from the void, confirming its gargantuan presence. But the ISW effect only confirms the void's gravitational influence. To truly understand its formation, we must turn our attention to the most exotic and least understood component of the universe: dark energy. If the KBC Void is a statistical fluke, a rare lumpiness in the early universe, then the standard lambda CDM model can, with some stretching, accommodate it. But if the void is a sign that the cosmological principle is fundamentally broken, then we must reconsider the very nature of dark energy. The timescape cosmology, which we touched upon earlier, is the most compelling alternative. It suggests that the expansion we attribute to dark energy is merely a local effect. But there are other, even more radical theories that attempt to explain the void by modifying dark energy itself. One such theory suggests that dark energy is not a constant, uniform field, but a dynamical field that changes over space and time. This hypothetical field, sometimes called quintessence, could have a lower energy density inside the void and a higher energy density outside. This difference in energy density would create a pressure gradient, actively pushing matter out of the void and accelerating its expansion. Imagine the universe as a massive, invisible ocean, and dark energy is the tide. In the standard model, the tide is perfectly uniform. In the dynamical dark energy model, the tide is lower in the region of the KBC Void, creating a local low-pressure zone that sucks matter out. The KBC Void in this scenario becomes a self-sustaining engine of emptiness, a region where the very nature of dark energy is warped and diminished. This idea is deeply appealing because it solves two problems at once. It explains the formation of the massive void, and it offers a testable prediction about the nature of dark energy. If future observations can confirm that the properties of dark energy, its equation of state, or how its pressure relates to its density, are different inside the void compared to the dense walls, it would be a revolutionary discovery, confirming that dark energy is not the simple, uniform constant we assume it to be. The KBC Void, therefore, is the ultimate battleground for the future of cosmology. It is the place where the standard model and its radical alternatives meet, and where the ultimate truth about dark matter and dark energy will be revealed. But the journey into the void is not complete without considering the most human element of this story: the realization that our entire existence is tied to this colossal anomaly. The void is not just an abstract concept, it is the environment that has shaped the evolution of our galaxy, our solar system, and ultimately, us. The low density of the KBC Void has ensured a relatively quiet, undisturbed life for the Milky Way. We have avoided the violent galaxy-shredding collisions that are common in the dense clusters of the cosmic web. This cosmic isolation has given our galaxy the time and stability needed for complex life to evolve. If the Milky Way had been born in a dense cluster, the frequent gravitational harassment and high energy radiation from nearby active galactic nuclei might have sterilized our planet long ago. The KBC Void is, in a profound and poetic sense, our cosmic cradle. It is the quiet, safe harbor in a turbulent universe, the emptiness that allowed complexity to flourish. The very fact that we are here, contemplating this 2 billion light-year hole, is a testament to its protective influence. This brings us to the final, most mind-bending implication of the KBC Void: the possibility that it is not unique. If the universe is truly lumpy and inhomogeneous, as the KBC Void suggests, then there must be other, equally colossal voids and superclusters scattered throughout the cosmos. The KBC Void is merely the one we happen to inhabit. This leads to the concept of the cosmic landscape, a universe where the density of matter varies wildly from region to region, like the peaks and valleys of a vast cosmic mountain range. Imagine a universe where entire civilizations could evolve in a dense supercluster, experiencing a much slower expansion rate and a much higher density of matter, leading to a completely different set of cosmological measurements. And another civilization, in an even larger void than the KBC, might measure an even faster expansion rate, leading them to believe that dark energy is even more powerful than we do. The KBC Void forces us to abandon the idea of a single, universal cosmology. Instead, it suggests a local cosmology, where the laws of physics are the same, but the parameters, the Hubble constant, the density of matter, the perceived strength of dark energy, are all functions of location. Our understanding of the universe, therefore, is not a universal truth, but a local perspective, a view from the bottom of a colossal, empty well. The next generation of telescopes will not just map the voids, they will map the entire cosmic web, giving us a three-dimensional, high-resolution picture of the universe's true lumpiness. They will allow us to test the timescape model, to search for the subtle imprints of dynamical dark energy, and to finally determine if the KBC Void is a cosmic accident or the rule. The journey into the void is a journey into the ultimate unknown, a challenge to the very foundations of our scientific understanding. It is a reminder that the most profound secrets of the universe are often hidden in plain sight, in the vast, silent emptiness that surrounds us. The realization that we are in a cosmic whole was not a sudden revelation, but a slow, creeping suspicion that began to solidify in the late 1980s. Before the KBC Void was formally identified, astronomers were already grappling with a phenomenon they called the local velocity anomaly. Imagine you are standing on a perfectly flat, still ocean. If you measure the motion of your boat, it should be zero. Now, imagine the cosmos. If the universe were perfectly homogeneous, our galaxy's motion, once the overall Hubble expansion is subtracted, should be close to zero, but it wasn't. Our Milky Way galaxy, along with the entire local group, was found to be moving at an astonishing speed, over 600 kilometers per second, relative to the cosmic microwave background. This is a massive, inexplicable drift. It meant that something colossal was pulling us, or something colossal was pushing us. For years, the focus was on the pull. Astronomers searched for a massive, unseen structure that could account for this motion. They found the Great Attractor, a region of space containing the massive Norma cluster, and later, the Shapley supercluster, the largest concentration of galaxies in our local universe. These structures were the gravitational mountains, the dense walls of the cosmic web that were tugging at our galaxy. But the pull alone wasn't enough to explain the full 600 kilometers per second. The math didn't quite balance. It was like trying to explain a boat's speed by only measuring the current on one side. There had to be a force on the other side, a region of negative gravity, a cosmic vacuum that was actively contributing to our peculiar velocity. This is the intellectual lineage of the KBC Void. It was born not from looking at the emptiness, but from looking at the motion of matter. The void is the gravitational antimatter of the great attractor. It is the colossal, empty space on the opposite side of our galaxy that is pushing us away, complementing the pull from the dense superclusters. The formal identification of the KBC Void came in 2013 when astronomers Ryan Keenan, Amy Barger, and Lennox Cowie published their seminal paper. They didn't just look at the motion of a few nearby galaxies. They conducted a massive systematic survey of the distribution of galaxies out to 1 billion light-years. They used a combination of redshift surveys and X-ray data to map the three-dimensional density of matter. What they found was a clear, unmistakable spherical region, centered roughly on the Milky Way, where the density of matter was significantly lower than the cosmic average. They calculated its radius to be about 440 megaparsecs, or about 1.4 billion light-years. This was the first time that the size and shape of our local underdensity had been mapped with such precision. The paper was a bombshell, but it was also met with intense skepticism. The primary reason for the pushback was, once again, the cosmological principle. A void of this size is so statistically improbable in the standard lambda CDM model that many cosmologists simply dismissed it as a statistical fluke, a misinterpretation of the data, or a local anomaly that would disappear with more comprehensive surveys. The debate centered on the concept of baryon acoustic oscillations, BAOS. BAOS are the sound waves of the early universe, frozen into the distribution of matter. They act as a cosmic standard ruler. By measuring the size of this ruler in different parts of the universe, astronomers can precisely map the expansion history. The BAO data, when averaged over large scales, strongly supports the cosmological principle and the lambda CDM model. The challenge posed by the KBC Void was that it suggested the BAO measurements were being skewed by our local environment. If we are in a void, the light from distant BAO rulers has to travel through a region of space that is expanding faster than the average. This disturbs the apparent size of the ruler, leading to an incorrect reading of the Hubble constant. The battle lines were drawn. On one side, the proponents of the KBC Void argued that the local universe is lumpy and our location is special. This lumpy universe resolves the Hubble tension. On the other side, the defenders of the standard model argued that the universe is smooth on the largest scales, and the KBC Void is either not as massive as claimed, or its effects are negligible. This debate has led to a fascinating new field of research, void cosmology. Scientists are now using sophisticated computer simulations to model the formation and evolution of voids in the cosmic web. These simulations, which track the gravitational interaction of billions of dark matter particles, are designed to answer the ultimate question: can the lambda CDM model actually produce a void as massive as the KBC? The results of these simulations are mixed, but generally supportive of the void's existence. While a KBC-sized void is rare, it is not impossible. the simulations show that in a universe governed by cold, dark matter, there is a small but non-zero probability of forming a 2 billion light-year underdensity. The void is a statistical outlier, but it is an outlier that is allowed by the physics. However, the simulations also reveal a subtle yet crucial detail: the shape of the void. The KBC void is not a perfect sphere. It is slightly elongated, or perhaps better described as a collection of smaller, interconnected voids. This complexity in its shape is a key piece of evidence, as it reflects the chaotic, non-uniform gravitational forces that shaped it over cosmic time. The KBC void, therefore, has transitioned from a controversial anomaly to a critical test of our cosmological models. It is the single largest structure that challenges the cosmological principle, and its confirmation would force a fundamental re-evaluation of how we interpret all of our cosmic data. But the story of the void is not just about its size and its impact on the Hubble constant. It is also about the strange, almost philosophical implications of living in a region of profound emptiness. Imagine a civilization that evolved in a dense, massive cluster, like the Coma cluster, where galaxies are packed so tightly that the night sky is a blaze of light. For them, the universe would appear to be much slower expanding, much denser, and their cosmological measurements would be entirely different from ours. Their concept of normal would be our extreme. The KBC void offers us a unique perspective on the concept of cosmic democracy. For centuries, we have assumed that our view of the universe is the universal view. The void shatters that assumption. It suggests that our perception of the cosmos is inherently local, a product of our unique, anomalous location. This realization has profound implications for the search for extraterrestrial life. If void galaxies are indeed the pristine, quiet, and stable environments they appear to be, they might be the ideal location for the long-term evolution of complex life. While the dense clusters are violent and chaotic, the voids are the cosmic nurseries, the quiet corners where life can flourish undisturbed for billions of years. The KBC void, in this sense, might be a sign that we are not just in a safe harbor, but in a region of the universe that is uniquely conducive to life. The journey into the void is a journey into the ultimate unknown, a challenge to the very foundations of our scientific understanding. It is a reminder that the most profound secrets of the universe are often hidden in plain sight, in the vast, silent emptiness that surrounds us. The next chapter in the story of the KBC void is being written right now, with the launch of new, ambitious space missions. The Euclid Space Telescope, launched by the European Space Agency, is designed to create the largest, most accurate 3D map of the universe, charting the distribution of billions of galaxies across a third of the sky. Its primary goal is to study dark energy and the evolution of the cosmic web. Euclid's data will be a game-changer for void cosmology. By precisely mapping the filaments, clusters, and voids, it will provide the definitive test of the KBC void size, shape, and density. If Euclid confirms the KBC void as a 2 billion light-year underdensity, it will be the final nail in the coffin for the strict interpretation of the cosmological principle, and will force cosmologists to adopt a more nuanced, lumpy view of the universe. Furthermore, Euclid will be able to measure the subtle distortions in the shape of distant galaxies caused by the gravitational lensing effect of the void. This weak lensing is a direct measure of the total mass, including dark matter, inside the void. By comparing the lensing signal to the distribution of visible galaxies, scientists will be able to create a high-resolution map of the dark matter content of the KBC Void, finally revealing the true composition of this colossal emptiness. But the most exciting frontier in void research is the search for dark matter annihilation. Dark matter is thought to be its own antiparticle, meaning that when two dark matter particles collide, they annihilate, producing a burst of high-energy particles, such as gamma rays. In the dense regions of the cosmic web, the signal from dark matter annihilation is often overwhelmed by the gamma ray emission from pulsars, active galactic nuclei, and other astrophysical sources. But the KBC Void, being so empty of visible matter, offers a unique, quiet background for this search. If dark matter is indeed annihilating, the void should be a source of a faint, diffuse glow of gamma rays, a signal that is not contaminated by the noise of galaxies. The void, in this sense, is a giant, cosmic dark matter detector. If future gamma ray telescopes can detect this faint, pervasive signal coming from the direction of the KBC Void, it would be the first direct detection of dark matter, and a revolutionary moment for physics. The greatest emptiness in the universe would be the place where the greatest mystery of the universe is finally solved. The KBC Void is a profound reminder that our understanding of the universe is constantly evolving, constantly being challenged by the unexpected complexity of reality. We began this journey with a simple question: why are we inside a cosmic hole? The answer has taken us through the greatest crisis in modern cosmology, the nature of dark matter and dark energy, and the ultimate fate of the cosmos. The KBC Void is the culmination of a long, slow realization. The universe is not a sterile, uniform machine, but a dynamic, lumpy, and statistically improbable place, full of surprises and profound mysteries. It is a story of humility, of realizing that our location is not typical, but anomalous. It is a story of triumph, of using this anomaly to solve the greatest crisis in modern cosmology. The final, and perhaps most poetic implication of the KBC Void is its connection to the ultimate destiny of the universe. If the timescape model is correct, and dark energy is an illusion, the universe is fundamentally different from what we perceive. The standard model predicts a universe that will expand forever, leading to the Big Freeze. In this scenario, the KBC Void will continue to expand, becoming even emptier, eventually isolating the Milky Way into a lonely island in a sea of darkness. All other galaxies will recede beyond our visible horizon, and future astronomers will have no evidence of a universe beyond our local group. But if the timescape model, motivated by the KBC Void, is correct, the global expansion is slower. This means the universe contains more matter and less dark energy than we thought. In this scenario, the universe might be poised on a knife edge, a delicate balance between eternal expansion and eventual collapse. The KBC Void, the ultimate symbol of emptiness and expansion, might be the very structure that saves the universe from an empty, cold death, by revealing the true, slower expansion rate that allows for a more dramatic, matter-dominated future. The KBC Void is the ultimate cosmic paradox. It is a region of nothingness that explains everything. It is the hole in the universe that holds the key to the ultimate destiny of all things. It is the silence that speaks volumes. Thank you for joining us on this journey. This is CosmoDepth, and the universe is waiting.